Okay, we try to speak in English because we have an English speakers.
Are you welcome to speak in French? No problem for the introduction.
I will try English, and if you don't understand me, I will switch to French. So today, Heinz Kabutz, Java Champions, is yours, for yours, author of Java Specialist newsletters and specialist on concurrency, will speak about phased and StampedLock, so high level of concurrency. As usual, about 1 hour, then questions and response. And today it's a bit special. We will just take a beer, and people who won't come with us at the restaurants for the rest of the day. Just before beginning, next session will be on Wednesday, another time. It will be the 21st of January. So have a happy New Year and happy Christmas. And for before that, an happy session with Kirk. Thank you.
So thank you very much for allowing me to speak, and thanks for being willing to give up your Wednesday evening for this. Really appreciate it. Always appreciate when people want to listen to what I have to say. So I was thinking whilst I was walking over, and it was a bit further than I thought, so I kept on walking faster and faster until I was, I'm a programmer, not a runner, not an athlete. And I thought, well, what am I going to talk about? Just the introduction. And I was thinking about the problem that I've got, because sometimes when I look for something that I don't understand, I go to the internet and I search for it on Google, and I end up finding one of my newsletters, which doesn't really help me, because I've got about 250 or so articles out there, and on all sorts of topics, from swing to concurrency to performance to Java language to all sorts of weird and terrible tricks that you shouldn't really use maybe, and it's kind of frustrating, because I want to learn something new, and I find my newsletter, which I know doesn't have the answer. And then what was even worse was a few weeks ago, I got this email saying that Doug Lee has given a keynote. I said, great! You all know who Doug Lee is. He wrote Malloc, and he's done all the Java to concurrency classes. I said, fantastic! Now I can find out what this is all about, what concurrency is all about. I can learn something, and he's going to talk about StampedLock. So fantastic, I can learn about StampedLock. So I'm listening to him, and it's really hard to understand him because the audio was terrible, and the video was like the wrong way around. And he gets to the StampedLock, and he puts up my slides. So I was like, this is great. I mean, it's just terrible. And trying to learn something new, and it's just, pointed to this doesn't help me. So this is a talk where I'm looking at two different topics. The one is phaser, other one StampedLock. Before we start, I'd like to show us of hands who of you is using Java. All right, good. Now, who of you is still programming in Java 1.1? One person, okay? For real. Okay, yeah. You're not the only one. I've got other customers. Who's still programming? I'm going to make a big jump to 1.4. So I don't think anybody's in between there. It's like 1.4, there you go. Anybody 1.5 looking at maybe 1.6? 1.5, yeah. 1.6? Okay. 1.7? Anybody lucky enough to be able to break their teeth out with streams? Yeah. Kirk sent me a piece of code a while ago, and he said, oh, this doesn't work. Any idea why? Now, I'm not the worst Java programmer in the world. I'm certainly not the best, but I'm definitely not the worst. And I looked at this code for about half an hour, and I had absolutely no clue, first of all, what it was going to do and what was wrong with it. And eventually, I refactored it, sort of just put things here and there, and eventually we got it working. But good luck with Java 8. That's going to be fun. Now, the phaser is a Java 7 construct. But for most of these constructs, they are backports. So if you need the backport, you can get the backport. But you don't really want to use it as a backport. It really is meant for Java 7. And the StampedLock is a Java 8 construct, but there is a backport for Java 7. So the 1.1 guy, in your spare time, you can, of course, research this. Now, I think you've had enough introduction from me. By the way, this is where Kirk and I give courses. So if you get tired of this view here, that's my view out past my conference room in Crete. So if you get tired of Paris, you can come there. But anyway. Okay, so the first question is, why do we synchronize at all? Now, we don't want to synchronize if we can avoid it, right? But sometimes we've got mutable state, which we need to manage. We can't always just copy everything. That's, of course, was fashionable for a while to make everything a copy, to have everything immutable, and to just copy the whole world every time you change something. But there does come a limit where you're going to overstress your garbage collector with that. And some applications have really a huge volume of data where you're not going to be able to simply copy everything. So I took some graphs of coarse-grained locking versus fine-grained locking, and this was basically doing a piece of work, taking my time with each core. And this was on a dual-core laptop, and you can see that there's lots of green, very little red, and a fair amount of black. And it's basically, because it's effectively a single-threaded application, I'm tag teaming between the two. Very coarse-grained, and it took 51 seconds. Now, when I made it very fine-grained, I ended up with a rather sad picture. It just was like, all the red. And it looks like it's only using 50% of the resources in the system time, but actually it's much worse than that. If you look at the total time, it did the same amount of work, but with lots and lots of locking, and we ended up being about 745 seconds as opposed to with the previous one, which was 51 seconds. So it's hardly comparable. Now, the problem we have when we have locking is we end up with voluntary context switches, which we all know is something we should avoid if we can. Because we get allocated time quantum, we say, we don't want that, give it back, and we get swapped out, and that's a really expensive thing to do. So if we can be without blocking altogether, that's better. This is the same without blocking, and we ended up finishing in 28 seconds. Now, since you're a performance interest group, or user group, this is, of course, nothing new for you. So what we want to do is look at some different systems or constructs that we have in Java 7 and Java 8, which you can use for improving, hopefully, your throughput a bit. Now, the first one is a phaser. The phaser is currently the only synchronizer compatible with fork join. Now, what I mean by that, if you read my very latest newsletter, I talk about a class called an interface called Managed Blocker. Managed Blocker allows you to possibly create additional threads inside your common fork join pool if your job would be a blocking job. And currently this is the only synchronizer within Java which does that. You can write your own, and if you look at my latest newsletter, you'll see an example of that. And there have been ideas to include that in the abstract queued synchronizer, in which case all of the other constructs, from semaphore to CountDownLatch would all automatically also be compatible. But at the moment, it's not compatible. So the idea with the synchronizer is we want to sometimes communicate state change between different threads. And the one that we start with is a very, very basic one called a CountDownLatch. The CountDownLatch is a synchronizer that blocks until we reach 0 on the countdown. So we might say we've got 5 services we want to start, and whenever the service is started, we decrease that until we reach 0, and then we know we're good to go, everything's going to work. Once you reach 0, everything is fine and you stay open forever. So what I want to do is to compare this against phaser so you can see how they differ. The CountDownLatch here takes a count as a parameter, and it's a fixed number of initial permits, and once you use them up, you can never go back. So it's like a once-use type of construct. And when you call a wait, or wait with a timeout, you're going to wait until you reach 0 or get interrupted, and then once it's 0, you always go through immediately. And by the way, this is a very small group, and you're welcome to ask questions at any time. Just stop me, put your hand up, or shout out, and we'll get somebody to translate from Frenchlish into English for me so I can understand you, and then I'll repeat it and we'll get the answer. So at any time, don't be shy, please ask. whenever you call count on, you decrease it by 1 until you reach 0. So what I did was I captured this concurrent animated tutorial that Victor Grazi put together. And if you watch it, you'll see this is a CountDownLatch size 4, and I've got a couple of threads. It could be actually more than 4, could be also less than 4 waiting. And once I call countdown 4 times, which you'll see now, I'll do that in a moment. You'll see here now, countdown 1, 2, 3, 4. And after that, the latch is open. But it's a once use, and then you throw it away. And if you want to do it again, you just have to make another one. This was invented in America, so they just throw it away when it's over. It's not like no reuse. We just throw it away. So if I want to wait for a service to start, I would say, get service countdown at a wait that waits until all the services have been started. And I might have a database I've got to start. Once I start it, I count down, and I might have a mail server I've got to start. Once that's started, I also call countdown. Now the countdown is just a number. It doesn't actually know anything more about it than just that it's decreased by 1. So it's a very, very simple class, and it's so simple that it's easy to understand, but to use it isn't so easy. I'll show you an example in a moment. We've got another one which I'll look at very briefly, which is called Cyclic Barrier. The Cyclic Barrier I've never used in production code. Anybody use Cyclic Barrier in production code? I've used you once, okay. So this is something you'll rarely use. The idea is to wait until all the groups are at a certain rendezvous point, and then we all pass through, and you can attach a runnable to it to be executed whenever that happens. Now again, this one has got a fixed number. You can't increase it or decrease it whilst you're running. And if one of the threads doesn't reach the rendezvous or times out, then the rendezvous is broken, and you have to now reset the rendezvous, the barrier. So that's the idea here. And we've got, again, a fixed number, which we use. We've got a wait, which waits for all the threads to arrive. And if you get a timeout, the barrier breaks. And it's after that, the barrier is broken. You have to reset it before you want to use it. This is how things work in Crete. I live on the island of Crete, which Creta, I don't know how you say it in French. And I was very happy, very pleased to read today that the other airport on the island is now considered as a minor airport and an unimportant airport, because my airport where I live is now the major airport of the island, which is really cool. So I can go to places more easily, like Paris. Well, it's not that easy, but it's possible. Now, what happens in Crete is the tradition is on Sundays, the family eats together. So you have all the families getting together. And you have to go. I mean, if you're a Cretan, you have to go to the family. You can't not go. You can't say, you know what, I want to go swim at the beach. Well, my boy, you first have to eat, and then 4 hours later you can go to the beach. But this is the thing. It's a rendezvous. If one of the people doesn't show up, there's going to be some questions. Where were you, Manolis? Why weren't you at the rendezvous? You now have a broken barrier exception. We have to go to find out where you were. Go look for you amongst the olive trees somewhere. Okay, so you've got a cyclic barrier again of size 4, and I wait for 4 threads to arrive. Once all have arrived, then that will go through. Okay, and you can attach a runnable to that executes every time. All right, so these are sort of 2 constructs which we've had in the past in Java 7. No, actually, this has been since Java 5. It's been around for quite a long time. And they are easy to understand, but not so easy to use. Right? Whereas the phaser, this is the new Java 7 one, is more difficult to understand, but also more easy to use. If that makes any sense. Now, Kirk looks at me very confused. It's the grammar faux pas. No, it's more difficult to understand, and it's more easy to use. You'll see why. So the phaser has a richer vocabulary, a richer interface. So it's got more flexibility. You can change the number of parties dynamically. In the Cretan family, 5 people have to come. If one of them dies, you've got a problem. And I don't know what to do then. They're like, or if one of them moves to Germany for work, you've got a problem. Maybe they put up a Skype window or something, and you can join the rendezvous like that. But with the phaser, you can say, well, he's gone to Germany, let's decrease the parties by 1. And everything's good. So you can change it over time. At any time, you can change it. Another thing which we've got here is that it's compatible with the fork join framework, which means that if you block a thread with a phaser whilst you're inside a parallel stream or whilst you're inside a fork join framework, it's going to actually construct more threads to keep the parallelism the same within your fork join pool, up to a certain limit. It doesn't just arbitrarily continue constructing threads forever. Well, it can, which can actually lead out of memory errors, but that's another issue. So we've got here the phaser. The phaser takes a parent and parties. And I'll explain why you need parent in a moment. You don't have to pass in a parent. You can just have parties, and you don't even have to have parties. Both these parameters are optional. And so if I register, then I increase the number of parties. And if I, right, and I can also bulk register lots and lots of parties. Now, the reason why we've got parent is that we can arrange phasers in a tree to reduce contention. We all want to reduce contention in our work. And so, as I said, we can change the number dynamically by calling register. You can already see this is now already getting slightly more complicated than the basic CountDownLatch. Arrive and deregister is what we call signal only. It doesn't change. Well, arrive will signal that you've arrived, but it won't wait at all. It'll just say, hey, I'm there, and continue. The thread will continue. It'll just say if the party's been here. Arrive and deregister also decreases the number of parties by 1. So it's a bit like saying countdown and decrease count as the arrive and deregister. Then the await advance is a wait only. So it waits, and it waits for a specific phase. So you can say, I only want to know about the 3rd phase or the 10th phase. Only tell me then. So a thread can await until you get to that phase. And if you look at this now, all the other methods that you see in Java util, they just throw interrupted exception. Whereas this one saves it for later. I'll talk about that in a moment. You can also wait interruptibly for a timeout if you want to, and for a specific phase. And you can say arrive and await advance. So this is signal and wait. So it will also save the interrupt. So if you get interrupted, you'll just wait until you eventually get through before, and when you exit, then you also at the same time will return with the interrupted status set within Java. And the last one is this one, on advance. I think that's the last one. And this last one has a method we can override. By default, it doesn't do anything. And on advance will say true or false whether we want to continue running with this phase or whether we want to cancel it. So this allows us to finish early. And there are a whole bunch of other methods for managing the life cycle. This is why I said it's more difficult to understand, because there are far more choices. Right. Now, let's say I want to have a certain number of threads start their work roughly together. I mean, obviously, we can't do it exactly together because it's always subject to when the operating system actually gives us time. But let's try and get as close as possible. And we want, on the first example, I'm going to show you how to do it with the CountDownLatch, and then I'm going to show you how to do it with the phaser. So this is the code for the CountDownLatch. It's a little bit ugly. What we're doing here is I'm first counting how many tasks I've got plus 1, because I want to have each of them wait, but I also want the main thread to wait until all the others have started and they're all ready to go. So I'm saying here, I make a CountDownLatch. Now, I didn't use the lambda syntax here. Excuse me on that one. It wouldn't make that much difference anyway. So what I'm doing is I'm saying new thread latch.countdown, and then I say latch.await. So I first decrease the count, and I'm saying latch.await to wait until the others have all rendezvoused at this point. And then I print out running, and I call run, and of course, what am I going to do about the interrupted exception? Nobody knows how to deal with that. I've got a whole chapter in my concurrency course on how to deal with it, because nobody knows how it works. Okay, so every time I start it, I sleep for a bit, and then I count down towards the end. Now, my point about the interrupted exception is a better way to deal with it is to say, if I get interrupted over here in my wait, I really want to keep on waiting until I have success. And before I call the run, I want to reset my status to be interrupted if I was interrupted. You probably didn't follow that. It's like legalese and... Okay, let me show you what the code looks like. Then you understand what I'm talking about. This is a very, very common coding pattern we have, or idiom, right? So I call latch.countdown. Then I've got boolean was interrupted equals false. Local variable. While true, I try latch.await. And if I'm successful and I don't get an exception, then I simply break out of this while loop and I continue. If I get interrupted exception, then I would say was interrupted equals true. So I remember that I was interrupted, and I go back and wait. Now, whenever you get interrupted exceptions, it is essential that you also, or it is essential that the interrupted status at this point is reset, so that you're no longer interrupted. It's also if you throw interrupted exception, you're never allowed to throw interrupted exception and have a thread that's interrupted. It's either or. You can be not interrupted, or you can be interrupted, or you can throw an interrupted exception, but not both. You can get some horrible live locks that way. Okay? So once we exit from here, hopefully eventually we'll be successful. Then we say, if I was interrupted, then I re-interrupt myself, basically do a self-interrupt, and then I do the task.run. So it's a lot of code in order to do something which is actually very common, a very common thing to do. Okay. Now, the run task with the phaser is, as I said, much easier to use. Because all I do is I make a phaser of size 1. I don't even have to know what the size is up front. I just make one for the main thread. Whenever I go through, I register another party to this rendezvous. And then all of this code we had before is a single method called arrive and await advance. That's it. I'm done. Much simpler. And then over here with the phaser, I can say arrive and deregister. Now, this leaves the party. So what I could do here is I could say, let's rendezvous a few times. Let's rendezvous 10 times or something with the phaser. Okay, now the phaser also knows how many phases you've gone through. This is why it's called the phaser. And what you can do is you can subclass phaser, override the on advance to say whether or not you want to look at the next phase or whether you want to cancel this phaser. And you can then use this over here, thread local random. Current, and so I make a current version of thread local random. This helps me to get faster random numbers because I don't have to have the thread contention on the math.random, for example. So what I do is I make a new color, random color. I change the color to this random color that does it within the event dispatch thread, so we're safe there. And then sleep for a random time between 500 milliseconds and 3000 milliseconds. So it's going to sleep for between half a second and 3 seconds. It's then going to change the color back to the default color and then make a beep. I'll put my volume up so you can hear it. And then sleep for 2 seconds and basically wait for everybody to get there at the same time. So some will change quickly, some will change slowly, but they'll all eventually change. And then I'll say while the phase has not been terminated. This is what it looks like. I've got all these buttons. They all start with a different color, and then they all change their color back to default until they've all changed. And if they wait for 2 seconds, and they start again. All the different colors change back to default, and they do it 3 times, and then it ends up being done. Okay? Any questions about phases so far? Now, One of the things I've never spoken about so far is tiered phases. See, the idea with phases, you want to be able to also reduce your contention. So what you can do is you can actually arrange them in a tree structure. It's a little bit more complicated to understand. This one is not easier to use. It's just more complicated and more difficult to use, but you can get better throughput by having less contention. So your parent doesn't know what children it has, but when the child is added, the parent number is increased by 1. So if the child's register party is bigger than 1, and once the child's arrived parties is 0, then one party automatically arrives at parent, right? So it's a little bit more complicated. I'll show you now in a little graph how it works. And basically, if I call arrive and await advance, I have to wait until all the parties in the whole tree have arrived. But because I can have different threads contending on different parts of the tree, we can get better or less contention. No, once the child arrived parties is 0, then you have one party arriving at the parent. So it adds them together. So I'll show you an example now, then you'll see how it works. So hopefully it'll make a bit more sense. A working example. So here I've got a root phaser of size 3. I make phaser C1. The parent is the root, comma 4. That's the parties. Phaser C2 equals new phaser root, comma 5. And then phaser C3 has got C2 as a parent, and it doesn't have any parties. So it's 0. And if I print out root C1, C2, C3, you can see that the phases are all the same. It's all 0 at the moment. The parties for root are not 3, it's 5, right? It's this 3 plus the 2 children, C1 and C2, which are direct children of the parent. C1 is fairly simple. C1 is just basically, it's also 0 have arrived, but parties is 4 because it's exactly that. It doesn't have any children. Then I've got C2. C2 should have parties 5. And the reason it's got parties 5 is because C2 has parties 0. If C2 had parties more than 0, then you'd have parties 6 inside C2. I didn't say this was easy. Okay, or logical. So if I make the phaser root with 3 parties, for example, and C1 is with 4 parties, that increases the parties in root by 1. So now I've got now I've got 4 parties, right? If I then add C2 with parties 3, it increases the parties in root by 1, so you end up with 5. C3 has 0 parties, and so because it's got 0 parties, it does not increase the parties in C2. Yes? No, it shouldn't do that. To be honest, I haven't tried that out. I'm pretty sure it should also increase. So, for example, if I now say C3.register, you should see C2 increase. And we'll quickly try that out to see if we're right. Where's my code quickly? So we'll call this phaser test. I'm going to just make this a bit bigger so the people at the back can see. I'll make it like 26. Normally what you do is you take the average age of the person in the room, and that's your font size. Okay. So if I print out C2, that's the one we really want to know about. because C1 is going to stay the same. It doesn't matter what happens to, and we'll print out also C3. And then I'll say C3.register, then I'm pretty sure that print them out again that C2 is going to also increase by 1. Okay, so right, so we're printing. What is this? Oh, of course we printed it out before. Right, so we print out. We see C2 is 5. And C3 is 0, and then C3 becomes 1, and so C2 becomes 6 parties. Right. The idea behind this is to reduce the probability of having clashes on the threads which are blocked, or possibly not blocked, but reading the values of the parties. I don't know if this really makes a huge difference in the world, but now the phase is the only synchronizer which is at the moment compatible with fork join, which means that if for any reason you block a thread, it will create another thread to take over from that. And it basically, when you construct the fork join pool, you don't specify the upper limit of threads. You actually cannot specify an upper limit of threads. What you specify is a desired parallelism level. This is saying how many threads do I want to have running at the same time in my system. And this is quite interesting because the number of threads that is used is the number of threads you get back from available processors. So if we say runtime.get runtime.available processors. On this machine, it comes back with a number of 8. I only have 4 cores, but I've got 8 hardware threads, so it says, you know what, we'll just make 8, no problem. It's only got a possible parallelism level of 4, unless it's a memory bottleneck test, but for CPU-based, it's 4, right? I can't really realistically expect a much better speed up than that, but it makes it 8 anyway, because that's the default. And on some systems, what will happen is that the available processors will come back as a number of sockets on your system. So you might have a machine with 16 hardware threads or 16 cores per socket, and you've got 32 sockets, and it goes, great, you've got 32 threads we're going to make for this system. So luckily this is configurable. Then it's not something you can, it's not something which is completely hard coded. But this is a parallelism level, and if a thread is paused, then what you can do is you can actually, if a thread is paused with a phaser, it will construct more threads to keep it alive. It's not really trying to keep it at 100% utilization. It's just trying to stop it deadlocking. So it'll construct a few more threads to keep it going. So here, for example, what I've got is I make a fork join pool, and I give it a phased action with 100. And phased action just basically recursively goes and makes more and more actions. Each of these actions is simply blocking on a phase until we all reach 100 phases. Right? And what you can see is the fork join pool on on my dual core machine has got a parallelism of 2, but you can see that it's made far more threads to try and maintain that parallelism. Now the maximum number of threads that will happen in the shared pool if you're using parallel streams in Java 8 would be 4 times the number of hardware threads by default. So it's 4 times your common pool. That's just sort of it's sort of a side effect. You can't rely on that. In fact, you can't rely on anything on these things. So here we've got these 3 synchronizers, and you can see phasers is a more flexible alternative to latch and barrier semantics. And the coding is actually, as I said, if you saw one example, is actually simpler, but to understand it's a bit more complicated because you have lots of options that you can use. Any questions before we move on to StampedLock? All right, so sometimes we want to have this option of having a read and write lock. This means that whilst I'm busy reading, no one can corrupt what I'm busy doing. And I can have lots of threads reading at the same time, but I don't want to have multiple threads writing at the same time. And the reentrant ReadWriteLock is a class which was given to us in Java 1.5, and it's one of those things like fairness where if you first see it, you go, whoopee, we've always wanted this. And until you start using it, you realize it doesn't really give us as much as we were hoping. I'll talk about the starvation in a moment, but the reentrant ReadWriteLock always uses pessimistic locking, which means that whilst I'm reading, everybody who's trying to write is going to get blocked. That's what I mean by pessimistic reading. I'm assuming the worst. Whereas StampedLock gives us optimistic reading. It's actually more like optimistic reading rather than locking. It's not really locking because it's optimistic. It's the opposite of locking. It's optimistic reads. And you can convert these to pessimistic reads if you need to, or to pessimistic writes if you need to. Write locks are always pessimistic. They're also called exclusive locks. Now, when you get a write lock, you don't have to write anything. You can also not write, but typically you'd be writing. Now, the way that ReadWriteLock works is you've got two methods that you call WriteLock and ReadLock. WriteLock is exclusive, goes to one thread at a time. ReadLock is given to lots of threads at the same time. This is much better if you've got mostly reads doing. But it's a little bit tricky to use because it's not so easy to judge when the ReadLock is going to be expensive enough to warrant using this pattern, plus, or this class, and plus, it's got some pretty serious starvation issues, as we'll see in a moment. Now, both locks are pessimistic. So here, for example, I've got a bank account, and I've got a reentrant ReadWriteLock that controls it. Note it's reentrant, so you can get the lock again if you've got it already. Makes life much easier if you're trying to code it. And then I'm using this typical idiom where I'm saying WriteLock.lock, try update the balance, and then WriteLock.unlock. And then I've got the get balance where I first get the read lock and lock it, and then return the balance, and then unlock the read lock. Now, this doesn't make sense to use in this particular case because the read lock is really, 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 really short. And you need to have at least 2,000 instructions for it to be worthwhile to pay back the cost of setting it up. But that's not the only problem with the rented ReadWriteLock. In Java 5, they coded it in such a way that they didn't really care who comes along. They just issued the locks without any sort of traffic warden, and so you could get some really bad starvation on the writers. I'll show you an example of that in a moment. When Java 6 they fixed it, and in Java 6 they now give priority to the writers, which means you can get the readers being starved. And I'll show you. This is more difficult to explain, but I'll show you by with a few by comparing to StampedLock that it really does happen. So this is Java 5, and in Java 5, what we're doing is we're going to acquire some read locks, and then we're going to try to acquire a write lock. But before we let go of all the read locks, we're going to ask for another read lock. Now, I've been enjoying my time in Paris the last 2 days. I've almost been run over about 25 times per day, right? Because there are these funny stripes on the road, and I'm not quite sure what they're for. Anybody know these white stripes? I think so. It's like Christmas decorations, or something is going on. I don't know what they mean. They certainly don't mean, they're certainly not pedestrian crossings. Maybe if they're for bicycles or something. But no one stops for anybody here. So they don't know about the read lock and the write lock example. Now, what happens is if I've got a read lock that's currently being issued, no write lock can be issued because there's a read lock. It's exclusive. But if a new read lock is issued before the previous read lock unlocks, you can stop the write lock from ever getting through. It's a bit like having pedestrians walking over the road, over the pedestrian crossing, without giving a gap, and then the car never goes past. Of course, this doesn't really work in Paris. It's never going to be a problem in Paris. So here we've got a couple of readers going in. And then a writer says, hey, I also want to have, so the red is the writer, it's going to come now. I also want to have a lock, please, please, please. And so they say no problem, but in the meantime, before the previous one comes out, the next one comes in. And so they keep on taking turns from each other. Okay. This can continue forever. No, not forever, because it's one day we're all going to die, but it's one day, indefinitely. I remember I was teaching my sons a bit of Java programming and my nephews, and I told them this is an infinite loop. They said, what, really? What does it do? What runs forever? Wow, that's so cool. And I said, well, no, not really forever. You know, it is going to stop sometime, you know, before the world ends. You know, it is going to stop at some point. But indefinitely going to continue. So Java 6, they changed that a bit, so we didn't get that anymore. And in Java 6, they changed it so that once you ask for a writer, no new readers can be granted. So you can see here, you've got the readers coming in. And now eventually a writer arrives, and now the writer is blocking any readers from being issued after that. Now I must just tell you a bit of history about this animated tutorial here, or animated tutorial that Victor Grazi did. He put this together quite a while ago, and I looked at it once, long time ago, and I sort of just, okay, click, that's all cool. And then Kirk and Victor and I did a talk together. I sort of elbowed my way into the talk that was supposed to be between Victor and Kirk. And but one of the things that I knew was that this happens from my experiments. And so what we did was we made sure that the code, this ReadWriteLock example, reflects exactly what happens in the ReadWriteLock. So if you take this concurrent animated and you run it in Java 5, you'll get one behavior. If you run it in Java 6, you get a different behavior. Okay, and it's actually pretty cool because what he did was he also wrote the same thing for StampedLock. And so he was clicking through, going. Yep, good. Battery dead. Okay, so he picked this up with this little animated tutorial. I think that's pretty cool. That you can actually pick up things like that. And so I wrote some code to demonstrate it experimentally. I'm not going to try and understand that code that they wrote in there. And then we sent that to Doug Lee, and he confirmed that it wasn't really a problem. The fact that after the Writelock is issued, they get issued one by one. And I actually, with these types of things, I'm happy if they don't touch anything, because they could badly influence the performance by just changing one thing in the wrong way. So rather don't touch it. Okay, so let's look at synchronize versus reentrant lock. Now, synchronize is very, very, very easy to code correctly. Synchronize this, do operation, you're done. With the lock, ReadWriteLock or reentrant lock, you've got this little idiom which people have an incredible problem with. I don't understand why. It's just a mental block, but they really, really struggle with this. They do this. They'll say lock.lock, lock.unlock, and they don't put a try finally. So if you have an exception that happens over here, you walk away holding the lock. It's like those old hotels that you have sometimes, which have physical keys. And you walk out and you leave it in your pocket. Oh, damn, I go come home with a key in my pocket. You know, it's like that. Now, I can still get into the room, but no one else can, right? Or they put the lock inside the try. Also wrong. Should be before the try. Or they put the lock without the try in one of the methods. So you have one method out of 10 which doesn't unlock. If you call that method with that particular with a particular thread, that thread can still use the system. But no one else can, because you walked away holding the lock. So even though this is really not that difficult, people still struggle to get these right. That's the right idiom. These are all wrong. When I was doing some of the coding with the idioms for the StampedLock with Doug Lee, he even made a mistake. Like I said, Doug, please be a good example. Do it the right way. Just do it the right way. He did the first one. I said, no. Just try finally, just to make sure that it's right. Otherwise people say, well, Doug does it, I can also do it. So the StampedLock has much better performance than the rented ReadWriteLock for reading. The latest versions also don't suffer from starvation of writers anymore. I picked up some really bad starvation, which luckily has been fixed. But if you thought these idioms were hard, these other ones are even more difficult, right? They are far more difficult than the rented ReadWriteLock. So you have to work far more to get it right. And if you make a small difference in the idiom, you can have a huge difference in performance. I picked it up and I was doing some tests. In the original version, they had a certain idiom, and just shortening the code path between the optimistic read lock acquire and the validate, just by shortening it a little bit, we got massive performance gains. Okay, now the StampedLock looks like this. You've got a WriteLock method that returns a long. So this returns a stamp, basically, a number. You've got WriteLock interruptibly, which also types along, but it is allowed to throw an interrupted exception. So this is very similar to what you would have in for example, your reentrant ReadWriteLock. Okay, these are all the methods you have for managing exclusive writelocks, or pessimistic writelocks. Now, each of the methods returns a number, which is a stamp. If the number is 0, it means that no writelock was granted. So it wasn't successful. It couldn't get a writelock. Now, when I say writelock, this will never return 0. It might deadlock, but it won't return 0. It'll always return a write stamp. This will always return a write stamp. But this one, try writelock, might return 0 if there is no writelock available at that time. And the same thing with the timeout. Now, when I say unlock write, I have to pass in a write stamp. Like if I pass in a read stamp, it's going to throw an exception. So it checks that it's also a read stamp. And what I need to make sure there is that I match it correctly. Also remember that the StampedLock is not reentrant. Now, there's one piece of code that I was writing with reentrant ReadWriteLock, and I thought, okay, well, that was easy. Let's do it with StampedLock. And I struggled for about an hour, and I thought, okay, this is not going to happen. Just dumped it. Forget it. It's not going to happen. Too difficult. Because I had recursive calls inside, and then you just very, very hard to do it right. The actual code you need to do to get it right would involve a stack of stamps, which would be ridiculous, and just forget it. Just use reentrant ReadWriteLock. And so the last thing is you can convert. You can try to convert your current stamp to a write stamp. So if I've got a stamp, I can say, try and make this into a write stamp. This is something you can't do with the rented ReadWriteLock. You cannot upgrade a read lock to write lock. If you try and do that, you're going to deadlock your thread. It's never going to return. Whereas here, you can try to do it. Now, you might not be successful, but you can try. I'll show you how to do that in a moment. ReadLock looks exactly the same, except it says read instead of write. Everything's the same, so we don't have to go into the details. Let's look at our bank account with a StampedLock again. So now, I'm not doing optimistic reads yet. I'll do that in a moment. But I've got a StampedLock up here. I've got a balance. And then deposit gets the write lock, updates the balance, and unlocks the write lock. Then get balance, I get a read lock, return the balance, and return and unlock the read lock. Okay. Now, when you're reading, it's a lot cheaper than the rented ReadWriteLock, but the writing is pretty similar. Now, what's the difference between these two? Between the using re-entering to ReadWriteLock or StampedLock and just making the balance volatile. So this is now much simpler code. All I've done is I've made the balance volatile to make sure that I'm reading the current value. I've got a deposit method which updates the balance, and getBalance does not synchronize, it simply returns the volatile. Any ideas what the differences are between the two? There are differences. Pardon there? Well, no, between the re-entered ReadWriteLock approach and this approach, or the StampedLock, or this and this. This is the same as the re-entered ReadWriteLock at this point, except we're using a StampedLock. But it's the same logic. Yes? Any ideas? Correct. Here the reading will never ever block, unless of course the hardware is blocking you. But there's never a concurrency construct, and the reason why is that there's no pessimistic locking here. It's never going to give you, it's never going to say, well, I'm busy updating now, so you can't read. Okay. Now, excellent point. So here's a question. What about the fact that balance is double? What happens if I run this on a 32-bit machine? Right. Now, there's a really nasty rule in the Java memory model that forces JVM implementers to, if it's volatile, to have atomic reads and writes on doubles, on 64-bit values. So you're okay with that. If it wasn't volatile, you'd have a problem anyway, but that would be one of the big problems. You'd have some really wonky values coming back. But because it's volatile, you're okay. It's guaranteed to read it and write it in a 64-bit, in a single operation. Sorry, come again? Well, why? Tell me why you're saying that. So? Oops. So what? What's going on here? Searching. Okay, back. Okay, so I think what you're getting at, if I can translate Kirk Keys into English, is Kirk's complaining about the fact that you could get a you could get a read whilst the write's happening. Is that right? Yeah, but you're synchronizing in between. Okay. So no, it's not. But that doesn't matter because it's a volatile value. Now, in this particular code, it's going to work, right? However, it only works because there are no invariants across the fields. Right? I've only got one field. So there's never going and there's no intermediate value. It's not like, you know what, I'm gonna take off the balance, then I'm going to see if it's negative. If it's negative, I'm going to throw an exception and set it back to what it was. Or something like that. There's no sort of rules that prevent a certain value from happening. In that case, you couldn't do this because you could see intermediate values. But because there are no intermediate values, this would actually work. It is actually correct. There's my point about the volatile, your point about having to be for 64-bit values, and also the access has to be visible. Okay, so for this particular class, it's complete overkill to do either of these StampedLock or re-entered ReadWriteLock. But here it starts getting a bit more important. So I've got a point. Now the point is made up out of X and Y. Let me show you the code, what it looks like before we start messing it up. So the code would start off as a normal point, right? So this is what the point starts with. Starts like, it's just a point. It's got a method called move, which moves it from one point to another. It's got a move if at, so it only moves it if it's at a certain point, otherwise it doesn't move it. And it's got a distance from origin, which returns math.hypotenuse x, y. So very, very simple code. Now, Everybody can understand this. This is not difficult. But you can see that X and Y belong together. If I'm at this position, and I want to go to that position, I go from there to there. I'm not going there and then there. I'm not going there and then there. I'm going from there to there. Where this matters is GPS coordinates. I might be in my old country, South Africa, where there are certain areas. If you are there, you have been hijacked. Automatically, police helicopters are deployed and they're trying to find your body. That's how it works, right? So you don't want to go accidentally from there to there and then woo, 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 police sirens, helicopters, dogs. You want to make sure that each plot is at the right position, right? So that's why the invariant is that X and Y belong together. We always want to have these together. And if we don't care about throughput and blocking, we just make everything synchronized. And if that's not your bottleneck, leave it like that. It is, because it's much easier than StampedLock. All right, let's look at it now let's look at what the StampedLock for the writing looks like. So as I said, the invariant is X and Y belong together. And what I do is I make a StampedLock. This is very similar to the bank account, but except that I'm now updating them together. At this point, you wouldn't be able to do a volatile read because X could have been updated before Y, and you would get dirty values. So, so I lock it and I unlock with the right step. Okay. Now that was easy. What is a bit more difficult is when you do a conditional state change. If the value is a certain value, then do something. Okay. So with what we're going to do now is we're going to try and update it, and if we're not successful, we're going to do something else. So what we do here is we want to change it, but only if we can. So what we do is we first make a read lock, because we don't want to get a pessimistic write lock unless we absolutely have to. So we first get the read lock. We then say that if the state is not the expected state, then we unlock and exit methods. Now, at this point, we don't really know. Well, now we know it's a read lock, but it could also be WriteLock later on. So when we say unlock, we just have the normal unlock method, which can unlock both read locks and write locks. We don't care which one it is. So we first of all make sure that the state is correct. We don't want to get a write lock because that's going to be exclusive and it's going to be slower in most cases. What we then try and do is we try and convert our lock, whatever we have, to a write lock. The only time this would not succeed is if I have two threads which both have a write lock because it's non-exclusive, and they both try to convert to write lock at exactly the same time. Then one will fail and one will not fail. One will pass. And so one that fails, it's a really very rare event that it will fail, but it can happen. If you try and do it with re-entered lock, it'll just always block up the re-entered read write lock. But here it's going to, one of them will pass, others will fail, but it will fail very rarely. And if we succeed, then all is good. So if the right stamp is not equal to 0, then I say my stamp equals the right stamp, and I say, and I update my state, and I break. I have to break, otherwise I'm going to keep on forever trying to update the values. And it's easy to make a mistake, leave out the break, and you can have a problem. Otherwise, what I do is I unlock the read, and I lock the write lock. And we try again. But now the second time round, I now hold the write lock. Of course, I can do reading if I want to, but this is now an exclusive lock. And again, if the state is not correct, it could have been updated, could have been changed in between these two statements. Like somebody else could have come in and modified it. So if it's not the same, I would again exit like before. And otherwise, I'm going to again call try convert to write lock. And when I do that, if the write stamp is not equal to 0, which it will never be 0 because I already have the write lock. And remember, it's not reentrant. So if I've got the write lock and I say convert to write lock, I don't have to unlock it twice. I only have to unlock it once because it's not locking it again. It's just getting the same stamp back. So if write lock is not equal to 0, I get the stamp. I set the stamp and I then update the state and I break out of there. So at most you'll try it twice. Right. Now let's do let's try and code this together to see what it looks like. This move was fairly simple. Stamp equals SL dot WriteLock. The love about IntelliJ, it sort of figures out what the class is based on what method you're calling. Final. Okay. Then we have try. You might be tempted to say, oh, you know what, it's never going to have an exception there. Just don't do it. Just don't do it. SL.unlock write with the stamp. Right? Very, very simple, relatively simple idiom that people would typically struggle with. I don't know why. And then we have the move of at with the synchronized, which we take out the synchronized. And now this is the one which is a bit more complicated. Now I'm going to try and code it, and we'll see if I get it right, because I get it wrong about 3 out of 10 times nowadays. It's a lot better than I started. When I started, it was like 8 out of 10. Now it's only 3 out of 10. Let's see if today is one of those 3. So I'm going to say, first of all, I'm going to get the stamp equals SL.ReadLock. So you've got to really pay attention, because if I make a mistake, you'll have to help me to get it right. I don't have test code to make sure that it works. You'll have to actually use logic. Now I do a try, because we always have to try. And finally, SL.unlock, passing in the stamp. Okay, so that part should be okay. This becomes a while loop. While x is old x, and y is old y. While that's true, long write stamp equals SL.try convert to WriteLock. I'm trying to convert it to WriteLock, my existing stamp. Let's put this on another line so you can see it. There. If SL.validate write stamp, if it's successful, and it's really, really important that I do this, that I say stamp equals write stamp. You forget that, and you're going to get an exception, because you're going to try and unlock the wrong stamp. Just small things like that make a big difference in correctness. You'll find that pretty easily, but this won't be like a showstopper. But so if this is, then we also do the write, and very important, we break out of the while loop. Else, you don't actually need the else, you can just put it underneath, but else just a bit more neat and tidy. Else, we're going to say SL.unlock. This has to be a read lock. If it's not a read lock, there's a problem. There's something wrong. Yeah, this will throw an exception to a read stamp. At this point, it has to be read, because the second time it just has to work. If it doesn't work, there's a bug on StampedLock. I could. It's just safer. So I could say unlock here. And the same over here, I could say unlock. Both will work. But this just has an extra check to make sure that it really is a read stamp at this point, but not a write stamp. And then I'd say stamp equals SL.WriteLock. Okay. Get rid of this other if statement. Now, I think this is correct. Don't see anything. Anybody see anything wrong here? Bit of a head scratch, isn't it? Yes? Oh, you could do that. You could do that. But the thing is that it's going to be an extremely rare event. So because it's really such a rare event, I'm just going to let it go. Yeah, but that's like, yeah, that's fine. It already is. Cool. You're done. It's very fast. It's over here. You're going to unlock, and you're going to. It's basically what we're saying here. We're saying, let's say for example that 99.9% we actually are not at this position, right? We're almost never at this position. So we almost never need a write lock. We don't want to pay the cost of a write lock, if we can avoid it, we can simply always use read locks. It's only when sometimes you're at that position we're going to now try and update it. If two threads happen to be doing it at the same time, one will win, other will lose. All right, I think this is correct. We'll just compare it to this over here, which should be. Where? Here. This one. Okay, so here I'm not trying to. I'm getting the write lock. I've let go of the read lock. Now I'm going to wait until I get it. So the first time I'm saying I'm never going to try again. I'm just trying once. If I've got the read lock, I'm going to try and convert it to write lock, which is going to almost always work. Otherwise, I'm not going to block. Otherwise, I'm going to simply unlock the read, take a stand back, get the write lock. Now, the second time around, once I've got the write lock, now I can check this without any worry because it's more powerful than the read lock. And then the second time around, it's going to come back immediately with the write lock. It'll always work. They can't. Oh, in between where? Between these two. That's okay. Because another thread in between here gets it. Another thread has it. I'll simply block until it's returned. And then I get it. And then I check if the state's correct. And if it's correct, great. Otherwise, I unlock and I exit. Okay, I'll show you another way of writing this, which would be easier to understand. Move of at easier. Read lock. If this is false, then return. Okay. Then and then we unlock the stamp. Okay. So if the state is not what we expect, we simply return. But you have to have read lock to get it to make sure. Then we say stamp equals sl.writeLock. And now we say again, try finally sl unlock. This one I'm actually going to use unlock write and unlock read this time because I can. So this is going to be unlock read. And here I'm going to say again, let me invert that now. If that's true, then I'm going to say x equals y, x equals new x, and y equals new y. This is much easier to understand, this code. No? Come on, it's easier to understand. Yeah? I get a read lock. If my condition is false, I return. This is not going to happen. And if I return or not, in both cases, I'm going to unlock the read. I then get the write lock again. If the state is true, now, of course, it can change in between these two lines. That's okay. But that's okay. Then I'll simply return again. Then I won't do anything. But if the state is true, I would update the x and the y, and I'd unlock the write. But now, I don't have the benefit of saying, well, my threads come in, the condition's true for what I want to do. Before somebody else comes and messes things up in between here, I'm going to try and upgrade it to WriteLock. That's what we're saying with this other idiom, this move if at. I'll give you a solution how to make this a bit easier in a moment. Okay. My first question was this correct? And I think it's correct, but it's not always so easy to know because, yeah, okay. Now, yeah, sorry. Have I written tests? Yes, I have. test whether this works or not. Yeah, you can probably use the currency torture tests. What are they called nowadays? JC stress you can probably use to really hammer it with different options. Yeah. So it's you know that it's impossible to test correctness, and it's even more impossible with threads. Yeah, that's also not really practical, because if people struggle with the normal try finally, they're going to struggle even more with this one. So I've got a solution for you, which I'll show you in a moment, which I think is not unreasonable. Yeah, so I don't want to give false hope on this one, because I took the initial StampedLock that they gave me, that they released, and I started hammering it and found problems. I found a performance bug, okay, where the Writelocks were being completely starved out, and then they fixed that. And then I found another bug where sometimes they just have lost signals, just deadlock by itself. Fixed that too. So the versions now work very nicely, but to test that your code is correct, well, stress test. Okay. Now, what about optimistic? That's what we all want to do here, is optimistic reads. And this has three main methods. And it uses something called, I think it's a load fence, somewhere along the line. And so what happens is the optimistic read will try to get an optimistic read lock. This might return 0, but we don't actually care if it returns 0 or not. We are optimistic. We're going to assume that it's going to work. So we first call try optimistic read. We then check whether a WriteLock was issued after try optimistic read was called. That's all we really care about. Now, they did something in Java 8. They've added some three native methods to unsafe, called load fence, store fence, and full fence, to really mess up our code. And because the reason why is we need stricter validation, stricter sequence validation, stricter ordering for sequence validation than the normal volatile reads would give us. This is why we've got now an explicit load fence, which is done as part of the validate. There was a hack that they used where I think they had it was a lazy set, I think. Lazy set, was it? Lazy set. So lazy set was like this undocumented feature of a load that would do a load fence, which a couple of people knew that this would happen. But that's been replaced now in Java 8 with an explicit load fence that goes in there. All right, so this is now the optimistic read idiom. This is the simple one. I've got a more complicated one I'll show you in a moment. Right? What we do is, first of all, we try to do optimistic read. Now this gives back a stamp, which might or might not be 0. Let's go through this one step at a time. So it might or might not be 0. We assume it's not 0, right? So we read our state, our fields, into local variables, into local fields. So I'm reading the x and the y, for example, into current x and current y. Afterwards, I check whether or not this stamp is valid. I say validate. And what this does is, what could happen is that I call up try optimistic read whilst somebody else is holding the Writelock. If I do that, then I basically have to, then it's just going to come back with 0. It's not going to do anything. It's not going to block. It's going to say, no, it's not going to work. Get 0 back. So it's sort of assuming the worst case scenario. If somebody else was busy writing, I have to assume it's dirty. If I get a good stamp back, and whilst I'm busy updating the state, somebody acquires the Writelock, even if he hasn't actually written it, even if he hasn't actually interfered with me, the stamp is no longer valid, and this would fail. Right? So in order to get this to be really powerful, really work really well, the code path between the optimistic read and the valid has to be as short as possible. If you have anything in between here that takes a while, it's gonna fail too often, and you're not going to have very nice performance. Okay, so if let's say that we did succeed. No, let's say we didn't succeed. So it doesn't validate. If somebody else might have written, then in that case we default down to a pessimistic read. Now here the retry would be a good idea. Okay, so we get to ReadLock, we update the state. No, so we read the state to the current state, the ones we've got up here, and then finally we unlock the read. Now of course when we get the pessimistic read, we always get the values. And then we would then do some calculation, and you can do the same thing with the distance from origin. Okay, so we can get optimistic read the current x and the current y, and then validate that, and then if that fails, we would do the ReadLock and get the values, and then unlock the reading and afterwards, and work out the hypotenuse. Now, as I said, the shorter code path gives you much better performance. And what also helps is if you is to sometimes retry a few times to do an optimistic read. It can sometimes give you better performance. So let's try that for a moment. So at the moment we've got our little one little line. We're going to just make this a little bit. You know, one of the good things about writing code like this is that you're never going to be out of a job. Long stamp equals SL dot try optimistic read double. Okay, so I'm first going to do the normal one, then I'll do the one that retries a few times, equals x comma current y equals y. And then I do if not SL.validate stamp. If it doesn't validate, I'll simply say stamp equals SL.readLock. It's a pessimistic lock. And I say SL.unlock read the stamp again. That's all very easy. And then current x equals x and current y equals y, and then I return the hypotenuse. I think that's correct. Yeah, that's okay. All right, now how do I retry? So there's one idiom that I thought up. You're probably going to... thank you. So that would not work. See how easy it is to make mistakes when you gloss over something. That's okay. Let's move on. You know. No, not at all. Not at all. No, because the validate, the optimistic read will, or validate will make sure it's correct. Okay, now, what if I want to retry? Now, you're probably going to hate this code. I'm just warning you. I'm going to use goto. Goto in Java. I like this idiom. I don't know. I really do like it. Okay, you probably hate it, but what I like about it is you get a really short code path, so you get fantastic performance. There and there. Okay. We define current x and current y up there without being set. Okay. I then say for I, if naught up to optimistic retries, which would be a constant, which probably want to have this. It must be as short as possible. Don't forget that. So I'm going to make this 5 retries. This should probably be tunable in some way, but for now, let's make it 5. And I then do this stamp here. So let's copy this up here. Current equals x, current y equals y. If validate, breakout. If I don't succeed, I say long stamp equals sl.readlock. And Okay, so there you go. So this is Heinz's idiom for retrying a few times. I want to have as few if statements as possible. So I'm just doing a for loop here. Try optimistic read. Very short code path until we break out. Try again, try again, try again. If we're successful, break out, jump down here, go to, return hypotenuse. Okay? Otherwise, if we don't succeed after 5 times, we now get the read lock, update the values, read the values in, unlock the read lock, and do the hypotenuse. Please don't get sick. I've got it here as well. I'll email this to you. Okay, now, performance. This is a performance user group. You care about performance, don't you? As I said, I started doing, I've been doing performance research for quite a while. My PhD was on performance already. And I came to France as part of my PhD and managed to convince a company to buy some of my code. And that was enough for me to continue studying for a whole year and live for a whole year in South Africa. It wasn't very much, but life wasn't very expensive in South Africa. So it was my first successful sale, was a company in France, in Toulouse. Anyway, so my research was all about performance. So it's always been that. I've always cared about that a lot. And I started looking at the reentrance ReadWriteLock in 2008 already. Found these bugs in Java 5, and Java 6 had other bugs. And then in October 2 years ago, Doug Lee released the StampedLock to the concurrent interest list, and the writer starvation was much worse using the same tests as I had. And there were also, as I said, some bugs, missed signals which could cause a deadlock. And now they've got a better version which doesn't have the same bugs anymore. So I ran this with some Linux version. I had it's two sockets, 4 cores, now hyper-threading. It's basically my Java Specialist EU server, which has about 1 million people, or not 1 million downloads of articles over the year, but that's not very much per day. So it's really not used very much at all. And what I found was that the reads had to be converted to pessimistic reads less than 10% of the time, but in almost all cases it was less than 1% of the time. It had to be converted to pessimistic reads. And that was only with a single try to read. Didn't have to really loop. I did loop, and it did improve it a little bit in some cases, but even without that, it was really good, the performance. How much faster is it than reentrant ReadWriteLock? Well, if you look at a single thread, right? A single thread, of course, will never have a conflict, so it should be very, very fast. And your read speedup is about 4 times over the reentrant ReadWriteLock, whereas the write speedup is almost the same, 1.08. That's why I said the write is not really going to give you a great benefit. So you might say, well, okay, even for 1 thread, it's better. Right. What about if I've got 4 threads? Remember, I've got 8 cores that are running on this machine. Okay, this is now a logarithmic scale on the left-hand side, and we see that if I've got 4 threads, this is optimistic reading, of course, and I've got 4 threads, 4 readers and 0 writers, it's 64 times faster. Okay. If I've got 3 readers and 1 writer, it's 11 times faster. The writing is actually a bit slower, but the reading is faster. 2 readers, it's 12 times faster. And now we get the funny one, which is if I've got 1 reader and 3 writers, it's 353 times faster. We'll get back to that in a moment. Let's see what happens if I've got 16 threads. Now 16 threads, what happens is you can see the readers are going down in performance as you go down. And then all of a sudden you get 1 reader and 15 writers, and you get the StampedLock being like more than 1,000 times faster. Of course, we know that that's nonsense. There's no ways it's going to be that much faster. There's no logical explanation for that. Well, there is, and there's a bug in ReadWriteLock, which I picked up, and this demonstrates it. It's a bit hard to explain the bug. I mean, I can't explain it. is like that. If you have one reader and lots of writers, you've got a problem with read-write-lock. But the moment you've got two readers, you're okay. But if you've got one reader, you get this really bad effect. So it looks like it's amazingly better. It is better. You can see the other graphs, how much faster it is. But it's not 1,000 times. And it's not going to be like 50,000 times faster. It's just nonsense. Okay, reader throughput with StampedLock. This is number of readers, no writers. Okay, so you can see the red is if it's linear to n cores, and the blue is what it actually is. So it's not completely linear, but it's not too bad. Of course, it's logarithmic scale, so it's not that fantastic. Here I've got Kirk's favorite graph. This is now the reader, the write throughput. I don't know how on earth I got that. I was copying and pasting titles, and I managed to get this one wrong. Writer throughput with StampedLock. Okay. One writer, I get nice throughput. Two writers, it comes right down here. But then it starts getting faster again, the writer throughput. It's kind of weird, isn't it? And this is a common property when you've got algorithms that use adaptive spins with non-strict preference. Okay, what happens is that the threads manage to sneak in when the thread's enabled but hasn't been awoken yet. And so you actually end up getting better performance opportunities when you've got more threads trying to hammer the same write-lock. It's kind of counterintuitive. If you look at the mixed reader throughput, so it's basically the number of readers. This is ignoring read-write-lock, because you know that that's broken anyway. You can see how it goes down as you'd expect the graph to go down. This is with 16 minus n writers, right? So you have, like, for example, 16 readers and 0 writers, 15 readers and 1 writer, and so on. So he'll have 10 readers and 6 writers, for example. So on an 8-core machine. If you do the same thing, the same graph, you look at the same graph, exactly the same, with the read-write-lock, you get this. You can see this pretty flat, but then over here, it's again demonstrating that bug in the read-write-lock. So the StampedLock performed very well in the tests, much faster than read-write-lock. It gives you a way you can do optimistic locking, but the idioms can have a really big impact on the performance. If you have a bad idiom, you've got a problem. I just want to show you one more thing, which I haven't got slides for, but that shouldn't stop you from listening. This may be a good thing, and that is I started putting together StampedLock idioms. I mentioned to you that we've got a problem with idioms being too difficult. So I thought, why don't we use lambdas for this, Java 8. So what I've got is I've got here a method called WriteLock, which takes as a parameter a StampedLock and a supplier of V for the job that needs to be done. Okay, and so what I do is I do the WriteLock, I return writeJob.get, and I finally unlock the write again. Now I can have lots of different WriteLock methods. The one takes a supplier of an object. I've got one that takes an int supplier, one takes a double supplier, one takes a long supplier, one takes a runnable that returns void. And what's really cool is that lambdas, Java 8, is smart enough to figure out which one of these 4 methods I want to call based on the return type of the lambda I'm putting in. So that's really, really cool. And if you go back to our point, now you can see this is the first idiom. We can make this a little bit simpler by saying StampedLock idioms dot WriteLock, and we put in a lambda, and we simply say x plus equals lambda, delta, and y plus equals delta. And now it doesn't want to work. What have I done wrong now? Oh yes, I have to pass them StampedLock. Thank you. What would I do without you? Thanks. Okay. So there we go. I forgot to pass in the value. So there you go. I pass in the stamp block and I pass in the code that needs to be done within the stamp block. So I don't have to have the try final anymore. Don't have to write it myself anymore. Just pass in the stamp block. So that's great. What about this one? The move if at. So what I need to do is I pass in a predicate to say this is basically my predicate over here. And I pass in the action that must be done if this is true. So again, I'll do this. I'll say stamp block idioms dot conditional write SL. I won't forget it this time. The predicate, which is the following, x is equal to old x and y equals to old y. And then the action, which is the following, x equals new x and y equals new y. And the rest I can delete. It's exactly the same. Every time I want to do conditional write, put this in. Predicate, action. And this one only has one method. It's very simple. It's got a Boolean supplier. It's got the runnable action. Now, I didn't have time to add more. You might also want to have other actions which return values. If you want to do that, add that. The difficult one was the move if easier. Move if at. Get rid of this move if at easier. This one is more difficult. Distance from origin. The reason it's more difficult is somehow you need to get these two values into local fields, into local variables, but you can't because they're effectively final. So you can't change them directly. And I showed this to somebody who I won't name, who works for Oracle and who talks about lambdas and all sorts of things about Java. And I had never seen lambdas before. This was about 1.5 years ago. And I said, please help me. I'm really trying to get this to be like the most effective way possible. The only thing he said, looking after my code, saying, those are bad variable names. That's all he said. I'm like, excuse me, what are you talking about? No, you shouldn't have variables called x and y. I'm going like, it's a point. It's a point. I mean, what's wrong with x and y? It's a very reasonable name for a variable inside a point, x and y and z. Come on. Anyway, so he didn't help me at all. So I won't name him because he didn't help me either. So eventually I came up with this hack, which actually seems to work quite well. It doesn't create very many objects at all. Because obviously what you don't want to do is to construct tons and tons of objects whilst you're doing this. Or at least expensive objects. So this works fairly well. What you do is you say double array current equals 0, 0. And then Kirk's shaking his head. Jean is shaking his head too. Bear with me. Return stamp block idioms dot optimistic read computation. The first thing we do is we pass in a stamp block. We can also pass in the reads the number of retries if you want to. That's optional, right? So I can say comma 5 if I want to do that. I then have a reader, and the reader does the following. I say current naught equals x, current 1 equals y, comma. It's all happening in the same thread, so I'm okay there. It's an object which is only seen by this current thread, so I'm actually okay. Obviously, I'm constructing a double array every time I'm doing this. But I'm only constructing the object array once, the double array once, and I'm using it inside here. Okay, and then I would save the action, which would be math.hypot current 0, comma, current 1. Get rid of all of this other stuff. Okay, and again, this is smart enough to figure out which optimistic read you want. And because I'm returning a double, it actually figures out that I want to, that this lambda I'm passing in is actually double supplier. Yeah, exactly. Bad variable name. Yeah, exactly. I did some tests the last time somebody suggested that and found that the arrays were slightly faster to be created than objects, yeah. But you would have to do that anyway if you've got other types. Obviously, this is only, I've got any doubles, but if I've got doubles and a Boolean, I'd have to have an object, a class in here. I don't know. I'm not going to argue with that. It's just a good answer for a question which I don't have an answer to. Well, object's also a subclass of object, huh? There wasn't a very big difference, but I don't even know if there was a difference. It was just a good, I didn't really find it to be faster to, put it this way, when I did a very, very basic test, it didn't appear that arrays were slower than classes. Okay? It's a very diplomatic answer. I should become a diplomat, a Java diplomat, a performance diplomat. We all know how these tests go. It's like, why don't you do that? Nah, forget it. Next one. Okay. Anyway, we do have to construct one object. And yeah, we could have here, we could use a class. Obviously, you do have to have an object. You know? You can't have, this has to be an object. It can't be just a shared object. That's not going to work. It has to be an object. And yeah, this works nicely. See, one of the nice things here is also we can the double array of 2 elements would be a nice size too, wouldn't it? It would be 16 bytes plus another 16 is 32. It's 36 bytes plus the length goes around to 40 bytes. So you're going to have a pretty good chance that you're going to be living by yourself in the cache line. At least not with another one like that. Okay, so that's it for my Java 8 idioms, the Lambda idioms. I haven't actually shown that to anybody. You're the first guys. You're welcome to give me better suggestions than what I've done. I'm very happy to incorporate them in my ideas. Where to next? This is, of course, where these things get talked about. There are about over 1,000 people on that list. And so it can be quite heated sometimes with interesting discussions and ideas. And just don't forget, if you're not on my newsletter, please do subscribe, javaspecialist.eu if you'd like to. And any questions, you're welcome to email me as well. Okay, so I've done some tests, but not proper tests. I was... Yeah. Well, the problem you have here, because it's the fact that it's lambda doesn't really help me all that much, because it still has to construct a new object every time you call this, right? Even if it's a lambda. And the reason why is because you're accessing fields. So it has to construct a new object. The nice thing with lambdas is that if I've got 2 lambdas, or if I create a lambda many times, it is allowed to give you the same lambda back every time. It's allowed to. But here it can't, because it needs to access the fields. So it's not actually going to have that optimization. So you're still going to construct objects. Write, what's it called? No. Write array. Write, read further. No. Okay. I'm sure it will be. If Gil does it, it'll be good. What was? Oh, right. Bad. Well, that can always be fixed, you know. Any other comments, questions? Not from Kirk, he's not allowed to ask questions. No, you can ask if you want to. You can also answer them though. I'll flip them back to you. Well, in that case, thank you very much for listening. I really appreciate it and for coming out on Wednesday night. Thank you very much.